Chapter 5.4 talks about similar triangles, and we already actually discussed similar triangles back in when we were talking proportions. But suppose these two triangles are similar. And this triangle has these dimensions for the length of its sides. Well, as you recall, let's say this is side A, this is side B, and this is side C. And we have a triangle over here we say is a similar triangle with sides labeled D, E, F. Well, if you recall from our proportions, we could say that the proportion of any two sides, so C over A, for example, and that's not a very good C, let's make it a little better. C over A equals D over E. We could choose any two sides and relate them to the same sides in the similar triangle. So I could also do B over A equals F over E. So if I know what the length of one of these sides is, suppose I say F equals 4, I know that, then I can figure out what these other sides are. For example, I could go A, or not A, I could say that D over 4, or D over F. So I choose this over that. I've got to choose this over that equals 12 over 8. So now I want to isolate D, so I have to multiply both sides by 4. Because 4 divided by 4 is 1. And that leaves D over here, so this equals D. So we're talking about 48 over 8, which looks like it's 6. Okay? So this then equals 6. So if I want to figure out what E equals, we can go E, may as well do it same thing, E over 4. I could go E over 6, but I'm going to go E over 4 again. E over 4 equals 14.4 this time over 8, because now I have to choose this side over 8 to match with this side over 4. So when you do this and you solve for E, you end up with 7.2. So E equals 7.2. So this is the dimension. So what we've done is we just kind of shrunk this down proportionally to this triangle here. So similar triangles are proportional. And then the other thing we're going to talk about in this chapter, well, really that's all you talk about in this chapter. But I think I'll do one more topic since we have a little more time here. So when we're talking right triangles, so this is a right triangle. One of its angles is 90. I'll say this is side A, this is side B, this is side C. Well, we talked about this before. Para, what do I do with para? Pythagorean's theorem. Pythagorean's theorem. Hopefully I spelled that right. You can always check me on the internet. I'll go ahead and check myself real quick. So Pythagorean's theorem says that the longer side, the hypotenuse, c squared equals a squared plus b squared. Remember when we were talking about irrational numbers and I showed you this idea. So I could demonstrate this, why this is, or one way of looking at it at least, is, and this is what the Greeks did. They looked at the sides of this triangle and say this is a triangle in here, the orange internal area with one side length 3, one side length 4, and one side length 5. Well then if you make a square with the same lengths on each side as this side, so that's a 5 by 5 square, then you count all these up, you're going to have 25. Okay, do the same thing on the 4 side. You have 4 this way, 4 this way, for a total of 16. Then over here you have 3 by 3. So the area is 9. Well, number of squares is 9. Let's talk about that way. So you see that 25 equals 16 plus 9, or 5 squared equals 4 squared plus 3 squared, which, if you recall, that'd be like a squared plus b squared equals c squared. And this is good for any triangle. And it led to the development of irrational numbers by some people and the drowning of those who figured it out. The first person through the breach always gets the worst of it. So there's the Pythagorean's theorem that we could use. Let's do an example where we solve a problem with Pythagorean's theorem. So let's say we have a triangle that looks like this. So it's a right triangle, and it has to be a right triangle in order to use Pythagorean's theorem. We know that this is 16. Maybe this is a 16-foot ladder we have propped up against the wall. How tall is this wall then? If the ladder, when it's stretched like this, is the bottom part is 8 feet away from the bottom of the wall. So how tall is this? And let's just call this side A. So we know that a squared plus b squared equals c squared. Well, let's say 16 equals c, and 8 equals b. So a squared plus b squared, which is 8 squared, equals 16 squared. So let's subtract 8 squared off of each side. So we're going to end up with a squared equals 16 squared minus 8 squared. Here I plug that in the calculator. 16 squared minus 8 squared equals 192. That equals 192 equals a squared. So we come over here, side A is related to that. Excuse me. Well, it can't be 192 because this side is the longest side and it's only 16. So that's one way you can determine you made a mistake if you think it's 192 for A. But this is a squared. So what do we have to do? We have to take the square root of both sides. Take the square root of that. We'll take the square root of that. And we're only looking at the positive root. So A then because the square root of a means that a times a, we're looking for what value we multiply that by itself gives us a squared. Well, a times a is a squared. And here we just take the square root of this, and we'll just use the calculator for that. So let me see. I think I have to type in the number first here. 192. I don't see a square root. So what I will do is raise it to the power of 1/2. It's the same thing as the square root. So the square root, you probably have the square root on your calculator, and you can check the result here. The square root is equal to this number. Let's round it to 13.9. 1 decimal place more, 13.9. So this is approximately 13.9. That makes sense. It's a little longer than this one, but yet it's shorter than the longest part. That's how you would use Pythagorean's theorem to solve for lengths of a right triangle when you know two sides.